now all know that the disks have rich substructures, and as a result, the community, instead of calling protoplanetary disks, people now more like to call it planet-forming disks, because planets can naturally carve substructures in the disk. And these substructures, from the surveys, they are ubiquitous, and they're largely dominated by ring-like substructures, just reflecting that, well, strongly hint that there might be planets forming that carve these gaps and rings. And now back to the solar system, and it has a much longer history of the people studying the solar system, especially although it's much older, the remnant, the history of the solar nebula can be preserved in the solar system minor bodies, the asteroids. And if we have the fortune to collect certain, and certain asteroids are fortunate enough to fall onto the Earth, and we are able to study them through meteorites. And here is one very common type of meteorite called chondrite. And if you look at and if you cut it, and from this intersection, you can see there are many of these round bodies. Their typical size is sub-millimeter in size. These are called chondrules, and they are known to have experienced flash heating in I think in minutes, and followed by rapid cooling in a few hours. And how they formed is still a mystery. There are many different theories, but there's no consensus yet. This is mainly known to planetary scientists as building blocks of planets, although astronomers tend to say, well, dust grains are the building blocks. And the other stuff, this more fluffy, more irregular shaped white stuff, they are called calcium aluminum rich inclusion, CAIs. These are the oldest materials that one can date in the solar system, and that's how the age of the solar system is from, which is 4.567 billion years. And relative to the CAIs, the chondrules are formed typically 1 to 3 million years afterwards. And again, the conditions for CAI formation is also a mystery, and has been there have been many studies, but there haven't been a consensus yet. And again, in this field, there's also a major new paradigm in the past, established over the past decade, which is this isotopic dichotomy. So the chondrules, or the chondrites, they can be roughly divided into two categories. This NC non-carbonaceous chondrites, these are dry, their compositions are similar to the Earth, and they are expected to originate from the inner, the asteroids in the inner asteroid belt. And there's also the so-called carbonaceous chondrites. They are more volatile rich, and they likely originate from the outer asteroid belt. And when people analyze the nucleosynthetic isotopes, they find that they can divide it. They are nicely divided, okay, in this diagram. And the interpretation is that in the early solar system, there is some physical processes which prevent the mixing of the materials in the early solar system. And that something has been hypothesized to be Jupiter, for instance, because the formation of the Jupiter may naturally block the materials from the inside and outside of its orbits. Okay, but there are also alternative explanations. But this has been of tremendous research interest over the past few years. And now come to magnetic fields. So why do we care about magnetic fields? We know that magnetic fields play a crucial role driving angular momentum transport, which means you drive disk accretion and govern the disk evolution and disk structure. Of course, the disk structure, disk evolution, and also the level of turbulence, these are crucial for understanding many processes of planet formation. And so that's how magnetic fields come into play. And so paleomagnetism is a way to look into this problem from a completely new perspective. Okay, and here is the outline of the talk. I will briefly talk about the magnetism of protoplanetary disk and the solar nebula from the theory, well, basically from the astrophysical point of view, and then I will talk about the basic principle of meteorite paleomagnetism, and then I will present the results, start from the earlier results and also recent development. Okay, and feel free to interrupt if you have any questions. And these early results are summarized in our recent review paper. And there are also recent development, one published, one is still in preparation. Okay, so I'll start from, so as I said, magnetic fields plays a dominant role in angular momentum transport. So in understanding the disk evolution, there are two ways you can transport angular momentum. One is you can transport angular momentum radially outward, and this is usually considered as some viscous transport. And at microphysical level, you require some level of turbulence, usually driven by the MRI, magnetorotational instability. And the other way to drive angular momentum transport is vertical transport, right? In this case, you must have magnetic field threading the disk, and as the disk rotates, you bend the magnetic field. But magnetic fields don't want to be bent, right? So they try to resist. And when they resist, it exerts a torque that tries to break the rotation in the disk. And in the meantime, the angular momentum is transported vertically through the disk outflow, through the wind. So this is vertical transport of angular momentum, and on the left is a radial transport of angular momentum, radially outward. So which one dominates? That depends on the disk microphysics, which I will come back later. But clearly, in both cases, you can see that magnetic fields is playing a dominant role in angular momentum transport. Of course, you can say hydrodynamic turbulence can also transport angular momentum. The current understanding is that they can, but they are not quite enough to account for the bulk accretion rate in protoplanetary disks. So generally, either way, you will need magnetic fields. And we can do a little bit of math, right? How to calculate this angular momentum transport. Of course, when you transport angular momentum, you drive accretion, right? And accretion flow, because in the disk, the specific angular momentum increases with radius, right? And so when the materials accrete, you have to lose angular momentum. And associated with the accretion flow, there is the angular momentum flux associated with the accretion flow. And in terms of the radial transport of angular momentum by, for instance, the MRI, that's mainly related to the R and phi components of the magnetic field, and they build up this stress tensor called Maxwell stress tensor, the R phi component of the stress tensor, which transports angular momentum radially. Or in this wind case, you transport angular momentum vertically. In this case, it's by the Z phi component of this Maxwell stress tensor. That's a mathematical expression, but physically is all due to the Lorentz force. And from both cases, you can see the accretion rate to drive accretion. It's roughly, and you can basically by balancing the angular momentum flux by accretion with either the radial transport of radial angular momentum flux or the vertical angular momentum flux, you can establish a relation between the field strength and the accretion rate, right? And when you do that, you find this is the expression for the radial transport, and this is for the vertical transport. And here R is the radius, and LZ here is roughly the thickness of the disk. Is usually a few scale height. Okay, and from here you can already see to drive the accretion rate, certain accretion rate, which one is more efficient? Usually we're talking about a thin disk, right? So this is about the vertical thickness of the disk. Usually this is much smaller than the radius, right? Therefore, given the same accretion rate, the wind transport is more efficient because for the same field strength, this one you have multiplied by r, and here you only multiply by the thickness, right? So in other words, if you have a fixed accretion rate, then wind transport generally requires smaller field strength than radio transport by the MRI. And there's a now, but in terms of when you do the meteorite measurements, you only get a scalar, which is total magnetic field strength. But here, the fields are decomposed into different components, right? So there must be some, you have to account for certain geometric factors. Okay, what's the orientation of the magnetic field, right? And those depends on the more detailed disk microphysics. That's the magnetic field configuration. And very briefly about the microphysics. And here, the protoplanetary disks we are talking about are very poorly ionized, right? And here, the bulk of the disk, you have to rely on the non-thermal sources of ionization, cosmic rays, X-rays, or UV. Okay, but they are typically relatively weak. Can only ionize the surface layer better than they can do for the midplane, and whereas only in the very inner region where the temperature is above, say, 1000 K, you can have thermal ionization of the alkali species, where you can boost the ionization fraction to about 10 to the minus 8, right? But for the rest of the disk, actually, the ionization fraction is much lower than that. So it's very weakly ionized. And in this case, the magnetic fields are not well coupled to the gas. And that will introduce some so-called non-ideal MHD effects. I won't go into any details, but there are 3 of them. And they depend on, they have different dependence on the density and also on the magnetic field strength. Basically, in antipolar diffusion dominates in low density regions. You have the rho square here, and ohmic dominates in the higher density regions. And the Hall dominated regime lies in between. And there's also this Hall term has a polarity dependence in the sense that if you change the polarity of the vertical magnetic field, every other term will change sign, but the Hall term will not change sign because J also is curl of B, right? So this term doesn't change sign. That means this term is a polarity dependent term. That means when you incorporate the Hall effect, the outcome of the disk evolution is different depending on whether the poloidal field is aligned with rotation or anti-aligned with rotation. Okay, just to mention this. And this is some earlier simulation that I did that incorporate all 3 non-MHD effects. And this is the aligned case. And if you can just focus on the last panel, which is the color is toroidal, the phi component of the magnetic field, and the lines are poloidal magnetic field. And you can see in the aligned case, this magnetic fields get strongly amplified due to the so-called Hall shear instability. Okay, and in all cases, you launch a disk wind, but here you also get field amplification. And the disk somewhat get asymmetric. And here in the middle panel, the blue region is accretion flow, and the red region is a decretion flow. The gas moves out, etc. And in the anti-aligned case, where the background vertical field is anti-aligned with disk rotation, there's no such Hall shear. Actually, it works the other way around. It tries to reduce the field strength, but in the end, you again end up with asymmetric configuration, and you're always dominated by the field strength is always dominated by the toroidal field, but the toroidal field strength in this case is about something like a factor of 10 weaker, okay, than the aligned case. So that's also something to be aware of. Okay, that's only that's the main part about the simulations, and now let's go back to connect to the paleo magnetic measurements. All right, because those measurements only give you an estimate of the field strength, right? So that's only available information. So what we do here is try to link the field strength with the disk physics, right? For instance, in the case of radio transport of angular momentum by the MRI, we already said there's a relation between field strength and accretion rate, right? And usually m dot is proportional to b square, right? So this, if you derive the B field strength, it's proportional to m dot to the 1/2. And then we also put in some geometric factors. Yes, your question? Okay, no question. And here is some geometric factor, which is the ratio of B phi over BR as midplane. I put it here. And then basically you can arrive at this relation. Okay, so you expect the field strength to be on the order of 1 Gauss at 1 AU, roughly speaking, for typical disk accretion rate. And in the case of wind-driven accretion, as I said, it's more efficient. It also scales with m dot as to the 1/2, but as it's more efficient, right? So it requires much weaker field strength. But also you have the geometric factors, right? That's related to the base, okay, the toroidal magnetic field as a wind base divided by the toroidal magnetic field as a midplane. And based on the simulation that I just showed, for the aligned case, this m is roughly 10. In the anti-aligned case, this m is roughly 1, right? So basically, in the aligned case, the estimated field strength is actually comparable in these two cases. But anti-aligned case, the field strength, midplane field strength can be much weaker. Right, so that's the simple relation. Of course, astronomers have been tried very hard to measure magnetic fields from disks. Right? These are the early attempts based on the principle that one expects the dust. Usually, the dust are not spherical. Right? When they are not spherical, they try to align their long axis perpendicular to the magnetic field. And so early, and that has been the primary way to probe the orientation of magnetic field in the ISM and star-forming regions. But at disk scale, this is before ALMA. Doing this is very difficult. There was tentative evidence showing magnetic field originally reported, but then later, it turns out that the overall field, the polarization pattern is inconsistent with magnetic alignment of dust grains, but they are rather consistent with the so-called self-scattering. And so this was a bit disappointing, but it's also reasonable because the disk is much denser and you can easily destroy magnetic alignment of dust grains. And another way is to try to find Zeeman effect. Okay. By the way, this grain alignment, you only probe the orientation, right? Even you see it, you only see the orientation. But to measure the field strength, Zeeman is probably the only way to do it. And generally, you want to rely on certain special molecules with large magnetic moment, and people usually choose CN. Okay, I won't go into the details, but usually you're looking for a circularly polarized signal across the line profile. Okay, and usually that requires the field strength of greater than 1 to 10 milligauss to be detected, and that is also an averaged field strength integrated over the line of sight in the CN emitting layer, and there are lots of uncertainties where CNs. Where you can find CNs and what's the abundance of CNs, etc. There are a lot of uncertainties, and so far there's still non-detection. And then basically you can calculate the upper limits, and so far the upper limits are consistent with expectations. Basically, the expected field strength is not strong enough to be detected yet. And of course,
may I ask you some questions? I mean,
oh, sure.
Yeah, sure. Just a very basic question. So for the last few pages, so you are talking about so how so that you predict the magnetic field in theory and how magnetic field will be observable, right?
Right.
My question is, so for your simulation, so you place ambient magnetic field somehow, and then you try to calculate or estimate how the magnetic field evolved by disk physics, or
right. That's right. Yeah.
Okay, thanks. So that means that so you showed some equations that also depends on the initial magnetic field strength too.
That's right. That's right.
Okay, thanks.
So the assumption is that the disk inherits some of the magnetic field during the disk formation process. And basically, in all the simulations we have, in order to launch wind, you must have some a poloidal magnetic flux threading the disk. And that's expected to be inherited from the star formation process. How much flux inherits, that's a different story. But in order to match the observed accretion rate, we can add appropriate amount of flux, magnetic flux, to match the observed accretion rate. That's the short story.
Thank you.
Okay. Let's see. Okay, the non-detection of magnetic fields doesn't mean it doesn't exist. For instance, we know that these disks are, especially in the young stages, are always launch very strong jets, and the presence of jets is already, you generally need magnetic field to launch and collimate the jet. Okay, and this is a nice work from Qinhui. And also from this particular source, I think Qinhui reported that there's also tentative evidence for magnetic alignment, if I understand it correctly. At later stages for class 2 disks, you generally do not have such grand design, nice examples of powerful jets and outflows, but people still detect evidence of this wind from the line profiles of this, especially in this case, the O1 forbidden line. There's a wider wings, there's a high velocity component, a low velocity component in which has a broad component, etc. These are all interpreted as evidence for this wind, which especially the high velocity component and the broad components require magnetic fields to launch it, because other photoevaporation is not powerful enough to do that. So magnetic fields must be there, but yet astronomically people have not found direct evidence of it. So that comes to paleomagnetism. So this is actually a very, this field has a very long history of more than 100 years, right? Basically, it's the inference of ancient magnetic fields recorded by planetary materials. And you're trying to, this is in the form of so-called natural remnant magnetization with several subcategories. And conventionally, it has been used to study the Earth's magnetic field preserved in the rocks. For instance, from this way, people have inferred that the Earth's magnetic fields have been flipping aperiodically many times in the history. And also that's how the plate tectonics get confirmed and firmly established. And the basic principle is quite simple. Basically, you have certain certain recorders, certain materials that can record the ambient magnetic field when they cool or when they crystallize or when they accrete with a certain proportionality. Okay, so this B paleo is the ambient magnetic field recorded. Okay, and this M is usually what you can measure from the lab. Okay, after you collect this meteorite, you can measure. Usually this M is magnetic moment. Okay, and there's some proportionality coefficient, and this coefficient, of course, is unknown. But then, since you already have the sample of the rock, right? So you can try to remagnetize. You can demagnetize, remagnetize that sample to do this experiment, to do some experiments to calibrate this chi. Okay, and then you can infer this paleomagnetic field from your lab. How exactly these materials record the field, that's a very complex process, and that's not my field of expertise. And basically that really depends on, you really have to analyze very carefully their thermal history, chemical history, and their all kinds of geological processes that they have undergone through. So, but usually I rely on my collaborators for this job. But basically it's a very careful business. You need a lot of expertise to do that. So these were historically applied to the mostly applied to the rocks, right? Applying paleomagnetism to meteorites started in the 1950s, but its nature and meaning was only understood in the past decade or so, because they're really complex, because the meteorites can have undergone a lot of processes that it took people many years to understand. And for instance, this is the instruments that people, the MIT Paleomagnetic Lab people use to probe. Basically, you have to peel off the samples, right, from the meteorite, which is actually where most of the labor work is taken, right? So this is mostly labor work. I asked them, right, what's the where you spend most of time in doing this research? They say most of the time is spent to get off the sample from the meteorite. That's and once you get them out, and you have to be very careful, right? Record where you get them out, what the orientation is, etc. And then they put on this device called conducting quantum interference device, I believe, SQUID. And it's, you know, the chondrules are already very small stuff. But the magnetic carriers inside the chondrules are even smaller, right? So this is also it's by itself is a microscope. You have to be able to measure the distribution of magnetic fields at a very small scale, right? This is the device. And by the way, Rosetta also have a magnetometer, which they also collected data from the 60P comet. Okay, so what are the pros and cons for paleomagnetism? So the advantage is once you have a measurement, you have a direct measurement of the total field strength, right? And this is unlike Zeeman. For Zeeman, you measure the projected field strength, right? But here you get a direct kind of in situ measurement of the field strength. And also for meteorite, you can date the meteorite so that you can have the age information when it formed. And also depending on the magnetization process, some of the process you can consider them to happen as instantaneously. For instance, if it's undergone some rapid cooling, right, then you can say it records the instantaneous ambient field. But there are some other processes that happen more slowly, for instance, crystallization that may take many years, or during some thermal operation. Then magnetization is acquired over longer times, and in that sense, you can say you measure a time averaged field, right? So depending on the magnetization process. And the disadvantages are also obvious, right? You only have the field strength, but you don't know the orientation. You don't know where it happened, okay? But we can have some educated guess, although you never know where exactly they get magnetized. And also you need to be extremely careful, okay? That what bothered people for many, many years to understand its meaning. I will give you some examples. Okay, and once we have the measurement, basically we can apply this measurement, B paleo, to plug them here. And then we apply, say, this relation. Of course, this relation depends on the location, right? I said we don't know the location, but we can have educated guess. For instance, for non-carbonaceous chondrite, we expect them to come from the inner asteroid belt. They are presumably formed around 1 to 3 AU. Right? For carbonaceous chondrite, they are formed in the outer asteroid belt. Presumably, they were originally at around 3 to 7 AU. Right? That's the best you can do. And assume we know the disk physics, right? So we roughly know the geometric factors. And then the remaining is the accretion rate, and that's something that you can constrain. Okay, of course, with non-negligible uncertainties, right? So that's the game that we play. And if you just have a single sample, what you can say is, okay, I can infer the accretion rate, and is the accretion rate reasonable, right? If the accretion rate is consistent with, say, 10 to minus 8, so that's per year, then we're happy, right? This is consistent, okay? But if it's off by a lot, then you have to think about, okay, what's wrong, okay? And if you have multiple samples, for instance, if you have one from the one non-carbonaceous and one carbonaceous, then you can start to build a accretion rate profile, right? You can see whether it's consistent with steady state accretion or something else. Okay, so that's the game that you can play. Okay, any questions here? Okay, now it's time to show some results. Right, this is an example. This is, I think, the first example with high fidelity measurements. This is the Semakona chondrite, and this is the chondrule, one of the chondrules. You can see its size is just a fraction of a millimeter. And in these chondrules, you can, under the microscope, you can find there are these kind of very tiny particles, okay? These are dusty olivine crystals made of nearly pure iron, okay? And their size, you can see, is much, much smaller, okay? As micron-sized particles, sub-micron-sized particles. And these are the recorders, okay, of the magnetic field. And they have the Curie temperature of about 800 Celsius. And basically during chondrule formation, we know during chondrule formation, they are heated to above 1,000 degrees Kelvin, and then they followed by rapid cooling. And so it's expected that during the rapid cooling, these chondrules are basically these magnetic carriers in the chondrules can record the ambient magnetic field. So these are record magnetic field during chondrule formation events. And to make sure, right? So this is one of the complications, because not just these particles can record magnetic field. There are many other components in a chondrule, which include other magnetic carriers, which may have lower Curie temperatures, etc. So the experiment, you have to try to demagnetize any other components, and what you want is that in the end you are only left with these ion particles that carry the original nebula magnetization. Okay, and to make sure you do it right, so suppose this is a big chondrule, and on top of it, this is a big chondrite. On top of it, there are many different chondrules. The expectation is that when these chondrules get magnetized, they should have record certain magnetic field strength, magnetic field orientation, but before they are incorporated into the parent body, they have random motion, random rotation, etc. So when they are incorporated into the chondrite parent body, they should have similar field strength but random orientation. Okay. So this is a test that you want to do, right? And if you cut one chondrule into two, okay, then they should have the same orientation. Okay, right? So this is the experiment that they do. So here is a plot basically showing the orientation, magnetic orientation recorded in individual chondrules extracted from this chondrite. So different colors, okay, means the different chondrules. And for instance, for this one, it's split into two. Okay, and when they are located in the same region, it means they have the same orientation. Okay, so these two have the same orientation, but different chondrules, you can say they have very random orientation. So this is the conglomerate test. Okay, basically it passes this test, which ensures that the magnetization is acquired before they are incorporated into the parent body. Right. This is very important because once you are incorporated into the parent body, there are internal geological process. For instance, if there's parent body dynamo, etc., they can potentially remagnetize the chondrules, and in that case, you have all the magnetization to be in the same direction. But this is not the case, meaning that you are indeed obtaining the field strength, the field recorded before they incorporate to the parent body, meaning very likely during the chondrule formation event. Okay, and this is the field strength obtained from this Semakona chondrite. Field strength is obtained is about 0.5 Gauss. And if you apply that relation, and if you assume that they are located at about 3 AU, and if you assume that BZ is aligned with rotation, then you find a perfect agreement, right? If you for 10 to the minus 8 solar masses per year, right? That's the field strength you expect. That's exactly what is obtained from the measurement. So this is great, right? So the measurement, this is the first time you can infer the field strength from the meteorite that shows agreement with theory. And this table diagram summarizes all the meteorites measured so far, as of the time we wrote this review. You can see there were only one solid measurement, which is this one, and there are lots of upper and lower limits. Okay, and here it also lists this comet 67P from Rosetta, which also gives you an upper limit with non-detection. But overall, we can see that in all these cases, okay, here we further divided into the meteorites with ages less than 3 million years after CI and more than 3 million years. Right? After 3 million years, always non-detection. And here you have some upper and lower limits. So far, it looks like the inferred field strengths are all consistent with theoretical expectation of wind-driven accretion with the aligned field geometry. If in the case of anti-aligned, you would predict that the accretion rate is 10 to minus 7 solar masses per year, right? Which is also consistent, but probably the accretion rate is a little high, right? Okay. And one more thing is that we can use this to infer the lifetime of the solar nebula. And how do we do it? Here you can, so the basic assumption is you link the presence of the disk with the presence of magnetic field. Okay, if you don't detect any nebula magnetic field, and you believe that this meteorite could have been magnetized by the nebula field, then you can say that the nebula field is absent at the age of this meteorite, and that gives you the constraint on the nebula lifetime. And here we focus on this angerite, which is a kind of achondrite, and the magnetization mechanism is a little different. If we ignore all these details, just focus on the ages, you can see the from this positive measurement of chondrules, right? The earliest time, okay, at least you can say by the time of the 1.2 million year, there must be some magnetization. There must be nebula field here, right? And this measurement tells that by the end of 3.8 million years, there is already no field. Right? So that gives you a nebula dispersal window or nebula lifetime to be 1.2 to 3.9 million years. So based on this LL control measurements, semicona, and this angerite measurements, that can constrain the lifetime of the inner solar system. And then based on this data point, you can also constrain the outer solar system. Yes, question.
Yes, would you just remind me of the unit of the horizontal axis? MA means mega year.
Oh, right. MA is mega year, right? Million year.
Okay.
Yeah, sorry. Okay. Right. So of course, this is based on the assumption that you link the presence of disk with the presence of magnetic field. But we can say that in the absence of magnetic field, you can constrain the upper limit of the magnetically driven accretion rate. And in that case, it's below 10 to the minus 10 years. And based on our knowledge from astronomical observations, if it typically for disks with such low accretion rate, it's already very, very old. It's close to the dispersal stage. Okay. All right. In the final few minutes, let me talk about some really recent development. So this is a summary about the data as of, I think, a few months ago. Okay. You can see there are a bunch of more data points. Okay. And this is showing you, okay, so this plot is field strength versus distance, right? And of course, we don't know distance, right? So for non-carbonaceous chondrites, we just place 1 to 3 AU, and for carbonaceous chondrites, we just place its location to be 3 to 7 AU, right? So this is how this plot is constructed. And here is field strength as a function of time, okay? Which is based on the age of this individual individual chondrules. And I think for this plot, you generally get the similar consistent lifetimes as before, but I want to highlight is these data points, right? Let me go to here, right? So this is, I think, this is the second example, right? You have a very concrete measurement of the paleo intensity. And the interesting thing is, so before you are talking about this is a non-carbonaceous chondrite with this field strength, and that's for the inner solar system. Now we're talking about a carbonaceous chondrite in the outer solar system, but you measure a higher accretion rate, a higher field strength. Okay, and this is where there's a problem, because our standard expectation. So basically, here's the data. Basically, at say 2 AU-ish, we have 0.5 Gauss. The outer solar system, let's just pick up, say 5 AU, you have about 1 Gauss. And the theoretical expectation is that the accretion rate should scale as b squared times r to the something like 5/2. Okay, and if you plug in those numbers, you find a mismatch in accretion rate by a factor of 40. Okay, of course there's a big range, right? It can be a factor of few to a factor of say 100, but there's a big range. So basically, the expectation is that field strength should decrease over radius, but here you see a field strength actually seem to increase in radius. And this actually, because of this dichotomy between non-carbonaceous and carbonaceous chondrites, it naturally hints for maybe this is related to a disk substructure, right? And so that's the speculation of that paper. And just very briefly, and since I've been working with my postdoc, Yuhiko Aoyama, to study planet disk interaction in MHD winds. And here is one of the simulations. Basically, when you have put in a Jupiter mass planet, it opens a deep gap. And in the wind-driven accretion scenario, this gap actually concentrates a lot of magnetic flux. Okay, and actually outside of the gap, there's very little magnetic flux. And if you look at the average field strength around the planet orbit, you can see over here, and because the field strength is dominated by BZ, it's dominated by B5, you have field strength in this units is about 10-ish, but here the field strength is close to 0, right? So basically with a planet, the field strength in the midplane can vary by a factor of up to 10. Okay, so that might be a evidence that supports the presence this paleomagnetic measurements. Okay, and finally, let me talk about the paleomagnetism of the CAIs, right? So CAIs, there are a lot of mystery about the CAIs, and so that's why it's very useful and very interesting to explore the magnetic aspects of CAIs, which would give you some very new perspectives. And again, this is from the CAI, and usually CAIs are found from the carbonaceous chondrites. And again, my collaborators identified there's this iron nickel metal from the CAIs, and they conducted the measurements. So basically, they identified 5 CAIs from this particular chondrite. From the 5, they are able to measure the strength, paleo intensity from 3 of them, and the other 2, they can only measure upper limits. Okay, so for those with measurements, the mean field strength is 1.5 Gauss, okay, which is not particularly strong. It's only modestly strong, right? And the other 2 have upper limits of 0.2 to 1 Gauss-ish. But okay, this is not final yet. And in fact, recently they found that they told me that these numbers, especially those with measurements, are probably lower limits. Right? So they are still trying to figure out the better normalization factors, etc. But if we, let's say, stick to this 1.5 Gauss results, there are some problem in interpreting paleomagnetism in CAIs, because again, if you go back to this relation, right? So we let's say we just take this 1.5 Gauss measurement here. Then the question is, where are they from, right? What radius? What's the location? That we have no good guess of it. We don't know about it because CEIs in the early time, they have people, we know that they have undergone the large-scale mixing within the solar nebula. So they can, in principle, appear anywhere in the inner solar system. And at early solar system, we know that corresponds to class 0 and class 1 phases. We know the accretion rate is much higher. And we also know they undergo episodic accretion, so accretion rate is highly variable, right? So we don't have a good knowledge about accretion rate. And what makes it more complex is the disk thickness, which is h, is also unknown. Because for class 2 standard PPDs, the disk temperature is set by stellar irradiation. Basically, the sun, okay, the star, illuminate the disk, and by balancing heating and cooling, you set the disk temperature. So disk temperature is roughly is reasonably known as a function of distance. But here, because of the high accretion rate, you can have viscous heating, which can make the temperature higher, and H should also be larger than which we adopt in the class 2 phase. Right, so this is also relatively unknown, and it depends on the accretion rate. So there are a lot of complications. And in particular, we know that these early systems undergo this FU Orionis-like outbursts. These are the outbursts where accretion rate can jump to 10 to the 6 up to a few times 10 to minus 4 years over just very short, like a year, less than a few months time scale. And then it can stay in this high state over tens or even 100 years. And it is expected that the protostar likely build most of mass through this kind of episodic accretion. And during the accretion outburst, it can release a lot of heat and can substantially heat up the disk, and it can this heating front can propagate to very large distances. For instance, this disk have been interpreted that this heating has been able to push the water snow line all the way to 40 AU. Right? In our solar system, the water snow line is just something like 1 to 2 AU-ish, right? But this one, it can push to 40 AU shortly after the outburst. So the theoretical scenario that we envisage is that the nebula is probably repeatedly heated by this FU Orr-like outburst and followed by cooling. Right? After the outburst, the disk cools, and so this heating front retreats. And CEIs, because of the recorders, magnetic recorders are mainly ion, right? And their Curie temperature is about 1000 K. So we expect the CEIs should be able to record the nebula field when they are heated above this Curie temperature. And of course, this process can happen many times. And the paleo intensity that we record reflects the last time the disk is heated above the 1000 K at the location of the CEI. So that's the physical picture that we envisage. And there's also a coincidence. Basically, this Curie temperature is roughly the same as the critical temperature to thermally ionize the alkali species. Right? Once these species are ionized, you can have very strong MRI, okay, to provide the source of viscous heating, right? Okay, and I also asked Bobo, who also told me that there's also evidence for disk heated to say 1000 K out to a few AU scale, right? So I think although there's not very direct evidence, it's already very encouraging, right? This process is likely happening. And so you can build up a model, right? That's the standard Shakura-Sunev alpha disk model, where you can include the role of viscous heating in an analytic manner. And so basically, this is the result of for different m dot, you can show the disk temperature as a function of accretion rate. Basically, the color is temperature, and vertical axis is accretion rate, and horizontal axis is the disk radius. Okay, you can basically get the temperature as a function of accretion rate, and 1000 K is here. basically the way to read it is at 1 AU, you can reach 1000 K at accretion rate of say a few times 10 to the minus 7 solar masses per year, etc. And assuming that this viscous heating is due to the MRI, there is a relation between the turbulent strength and the field strength you can obtain from the MRI. So from there, you can have the field strength, right? So these are the contours of constant magnetic field under this scenario. And so the intersection of 1000 K and this constant field contours gives you the relation of the expected field strength as a function of radius, right? So we arrive at something like 200-ish Gauss. Okay, so this is, sorry, 200-ish microtesla. This is the units that the planetary science people use. So this is about 2.8 Gauss. So given the expected accretion rate and considering uncertainties, we can anticipate that the field strength to be around, that's basically 0.3 to 2 Gauss, okay, at least in excellent agreement with the measurements. And this would translate to a radial distance about 3 to 30 AU, right, in these cases. All right, so this is just one possible explanation, but we'll still have to wait for the update regarding their normalization factor, whether that 1.5 Gauss measurement remains robust or not. Okay, so this is the end of my talk. Let me just summarize. So magnetic fields carry important clues about nebula evolution, and we basically link this nebula field strength with the accretion rate. And there are some geometric factors can be calibrated from microphysical simulations. And paleomagnetism has some unique advantages over astral measurements. And the handful of measurements so far, so the field strength is generally consistent with theoretical expectation. The nebula has a mean field strength, likely consistent with this aligned geometry. And there's also placed upper limits on the nebula lifetime. The new data hint on a substructure between the inner and outer solar system, potentially due to Jupiter. And there's also the first paleomagnetic measurements of the CEIs, might represent evidence for episodic accretion. And here's some outlook. And I think we still need to improve our theory about the short-term dynamics as well as long-term evolution with realistic microphysics. And it would be really nice to have independent constraints from astronomical measurements, especially from Zeeman or GK effects. And from paleomagnetism side, there are several groups of people. They are trying to make the measurements from more chondrite groups, doing measurements for more CAIs, and there are also plans for spacecraft in situ measurements, and also I think the sample return missions also have, once you have returned samples, you can also study paleomagnetism from those samples. And I will stop here. Thank you very much.
Okay, thank you, Xuening. So anyone has any questions?
Yes, there is. Yeah, thank you very much for the nice talk. I have a quick question about the B field, whether the B field is uniform or not. You mentioned about the substructure, like the planet influence on the B field strength distribution. And I'm just curious, when you talk about MRI, what's the scale where you can have uniform B field, or I mean, are they also expected to have a very non-uniform strength?
Okay. Okay. So thanks for the question. Right. For the measurements in the inner solar system, generally, the MRI is suppressed here because you have very strong non-ideal MHD effects, and and in this case, the field configuration is largely laminar, and you won't expect very much changes of the field strength. Well, I'm not saying it's uniform. At least it should vary relatively smoothly. But there is one caveat, which is because the dominant component is, let me go to the earlier simulations. Right, because the dominant component is always the phi component, and there are regions where the phi component of the field changes sign. Okay, this could happen in certain regions of the disk, and that's one caveat. Basically, the field strength in most regions it should be relatively smooth, but in certain regions it may change sign abruptly. But if you were talking about, say, within 10 AU, you know, in this simulation, this happens beyond 10 AU. If you're just talking about this region, the expectation is that it should be mostly smooth, right?
Thank you very much.
Yes, no problem.
Rachel Fei?
Thank you, Xuening. Very good talk. I have a question. Actually, I have a few questions. So the reason that you choose to have this 10 to the minus 8 accretion rate is because you want to apply to the PPD, right?
Right.
Not for the early phase, right? So I'm curious about whether these chondroids can be formed in the early phase, like the class 0 phase or a 1 phase, where the accretion rate is much higher. Would that be possible to form chondroid in that early phase?
Yeah, well, of course. So let me go to, yeah. Right. So for one thing, if we believe this ages, the age of this semiconductor chondrite, it's not that young, right? It's more than 1 million years after CEI. Usually, these disks, their accretion rate is, yeah, generally you won't expect it to be much higher than this 10 to the minus 7, right? And so overall, I think for disks around this age, the general picture we applied should still be a reasonable picture. I think the main new element in the early phases are, one is this episodic accretion, and the other is the possibility of the gravitational instability. But these may be related. But in both cases, as long as it's the magnetic field that is dominate the disk accretion and transport, the overall interpretation framework should work reasonably well. But one caveat is regarding the chondrule formation mechanism, which is not something that we completely understand, right? Here, it basically assumes that although the chondrules are heated to very high temperature, we still assume it records the ambient magnetic field in an unperturbed disk. Right? In reality, if the ambient medium is also heated to that high temperature, whether the ambient, okay, what happens in the local environment at the chondrule formation event, that's something we don't know, right? This is another caveat. We are still assuming the disk itself is intact during chondrule formation event, right? I hope that answered your question.
Okay, I kind of get it. From another question is, so this measurement is actually from the chondroids, right? So it's a kind of microscopic measurements, right?
Right.
But we're talking about in the observation, we cannot measure that. I mean from the, of course, we can measure that. But how about for large scale diffuse strength? I mean, kind of the same as the micro scales. I mean, the strength, expect the same.
Okay, so you are talking about the field strength at the
Larger
large
scale.
the large
Larger-
scale field strength versus the field strength the micro
micro-
scale.
Yeah.
Okay, field strength. Right. So here the expectation is they should not be that different because the you have very strong non-ideal MHD effects, which essentially will smear out any small scale fluctuations in magnetic field. Right. So the large scale and small scale shouldn't be that different, unless the large scale field changes abruptly. But even they change abruptly, it takes place over a large scale. It's not like, say, MRI turbulence you have in the ideal MHD setting where you have MRI turbulence, you have local current sheets where magnetic field changes very dynamically. I don't think that is the case for the bulk inner region of the disk due to all these non-ideal MHD effects.
Okay. Okay. I think I know. I think there's even the microscopic scales. I mean, the field lines actually align with those large scale structure, right?
Yes. Yes.
Okay.
Yes.
Okay. Thank you.
Hiro Takami.
Oh, thank you for a very nice talk. And the first question is about, I mean, you mentioned the Fourier type outburst and, the disk heatings,
Right.
so towards 1,000 Kelvin.
Mhm.
But those objects are also associated with a very large massive accretion rate.
Right.
So I'm wondering, so how much are you sure, if the, so this, solid materials so remain? I mean, after after the Fourier type outburst, until the entire lifetime of the disk, how much are you sure? So some materials so would remain in the disk. All right, so in some, so yeah.
Okay. 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 So I guess your question is because they're very strong accretion, most of the stuff should just get accreted together with the gas.
Yeah, that's right. Yeah, for the stars.
Right.
And maybe, yeah, of course, so even in class, it's class on phase. So we also, so get envelope, some accretion from the envelope to the disks. So in the entire lifetime of the so protostar evolution, maybe all the material will be replaced. At least for those in class 1 phase. What do you think? Sorry, I'm not so fully sure. So I won't ask you your opinion.
Okay. Yeah. So for CAIs, I think one important question about CAIs, which is also a long-standing question about CAIs, is how CAIs are formed at first place, right? So forming the texture and composition, yes, to having the textures like the fluffy and I think basically from the geological point of view to form CAIs, you have to be also rapidly heated to something like 2000 Kelvin, okay? And the expectation is that has to be happen very close to the protostar. And then the CAIs are usually found in the carbonaceous chondrites, which is in the outer solar system, right? So the two long-standing questions is how CAIs get formed and how CAIs end up in the outer solar system. Okay, so that's the two questions. People don't have the answer, but there are various theories. For instance, Shen, the X-wind model is one possibility, right? They are formed in the inner and then they are ejected by the wind and they are launched to the outer region. And there are also other models saying there's some internal transport through the disk, right? There are meridional flows, for instance. Of course, during the rapid accretion, a lot of stuff must get accreted, but there must be some remaining stuff that get transported outside. So that's a question not fully understood, but the fact that we have CAIs left, and they are found in the outer solar system already suggests there must be some large-scale mixing, and not all the CAIs get swallowed by the star. And how CAIs are magnetized is in fact a different question, right? But it potentially can help constrain the scenarios of CAI transport and formation.
Okay, thank you. Another question is, so some people believe the solar
Mhm.
system small bodies have changed their orbit so much, even after 10 mega year time scale. So so I mean, even after the most of the gas and dust so dissipated because of but they may still so they can be affected by gravitational perturbations so by gaseous giants, and so some people develop models for those processes, like so Grand Tack model, Nice model, and so on.
Right.
And my question is, how much is your study affected by those kind of processes?
Right. I think the right. I think here. So where are these numbers coming from? 1 to 3 AU and 3 to 7 AU. And I think these numbers come from the Grand Tech models. The short answer is
Okay,
the
okay,
short answer is that we don't know, right? We don't know. But based
okay,
on the Grand
okay,
Tech model, yeah, they are likely to be at that there before the Jupiter starts to migrate, for instance.
okay, okay. Thank you very much. Okay, so that effect is included at least. Yeah, okay.
Right.
Okay, thank you.
No problem.
Okay, so I see another question from Indrani. So
Yes. So hi, Xuening. Thanks for the interesting talk. So I was wondering where you mentioned the Curie temperature is similar to the critical temperature for the MRI to kick in. So what happens at that zone? Yeah, it was mentioned that the CAI can record the nebula field. So do they measure the enhanced magnetic field, because the temperature is similar, so it leads to the strong turbulence? So can you please elaborate it?
Oh, right. So here, the the model is a standard viscous disk model, and in that model, the alpha is and here I think standard value we take is 0.03, but that's something you can adjust. And in the MRI turbulence, there's a relation which is the alpha times beta. Beta is the ratio of gas pressure over magnetic pressure. Okay.
Yes.
And this alpha times beta is about 1/2. Okay. So that's that has been calibrated in many MRI simulations. So basically, there's a direct relationship between the strength of the turbulence and the alpha value. And this is how this equation is coming from. And of course, in very strong MRI turbulence, the field strength is highly dynamic. There's a distribution. There are regions with stronger field and there are regions with weak field. And that relation represents kind of a mean field. But it is possible that the CAI could experience fields stronger than that, but I would not expect too much stronger than that. I think a factor of at most a few. I'm not sure whether that answer your question.
Yeah, thanks for the explanation.
so anyone has further questions? Indrani, you still have the hands up?
Oh, no, sorry, I'm turning it on.
Okay, so yeah, so I'm just wondering about the CAIs you took measurements from. So that's from Mocha meteorite, right?
No. The CAI is not from the semicolon.
So
This is
where it is from?
This one.
So it's a from CO chondrite.
Right, it's a CO chondrite.
Okay, so yeah, so it could be let's see. So how do you know how big that is? So this is a very small CAI. So that if the size measurement is labels, right, it's 10 micron, 10 micron. So this CAI if will be about at most 100 micron size. No, 50 micron.
Probably, right? Uh,
Right. So and are they about the same size? For the iron nickel grains?
Oh, this iron nickel grain is much smaller, I think. Yeah, this is micron size.
Right.
Sorry, so what is your question? So why
Yeah.
are you
Yeah, I'm just
asking
wondering
the
about
size
how
of the
big,
CI?
how is whether the correlation between iron nickel grains in this specific CAI and their size of measurements. So whether the size measurements of CIs you are reporting is from a certain size range and a certain contract class. So you are labeling here as a CO contract. Okay.
Yeah.
So you
Yeah.
do have
Yeah.
the
This is. Sorry. Yeah.
so the 5 measurements are about the same. Let's see.
Right. They all come from the same contract. It's a lot of labor work where they managed to get out of 5 CAIs out of this contract, and then they also split one contract into 2 to make sure that, yeah, to pass the conglomerate test. Right. That's what they did.
Right, right. So yeah. So yeah, so for CO contract, you have already much fewer, a lot fewer CAIs in this kind of contracted group. And so it may be a really rare event that you see those CAIs. So
I think the important thing is to identify the presence of this iron nickel metal, and I think not all the CAIs you can do that.
right, a lot of CIs do have iron nickel grains. So it's not like, but the question is whether you can infer those measurements and whether those actually correctly record the field, magnetic field that's experienced when it passes through carry points. Right.
That's also my understanding. I mean, the geological aspect of this, that's way beyond my expertise. I have no intuition which contract is good for this kind of measurements. Right? I know they wanted to do this for a long time, and only recently they managed to do it. So I'm sure this is not a very straightforward task.
Right, right. I do understand this is difficult, right? But I'm just curious about this CO contract or what the implication about this CO contract, because when you have really few CIs that you can infer from this contracted group, that means it may not be, you just don't have a lot of CIs doing this group, and then whether that's represent the class. So that's my general questions about this interpretation. Okay, I know it's a very delicate experiment, but just
Right.
yeah. I'm not sure that's but it could have different interpretation too.
Right.
So, but it's interesting. You
Right.
actually can infer the location.
Well, hopefully, yeah. If this model is correct, yeah.
But you agree that's model independent, right?
Yes, I agree. Yes, I admit that. Yeah.
Okay.
Yeah.
So, anyone else? Well, but then Xuening, it's really exciting. Okay, so for learning those measurements, how you were able to explain that with your models, and I think that's a very nice comparison. So
Yeah.
yeah, so and thank you for agreeing to talk. That's really nice.
Okay, thank you very much.
So anyone has a further question for Xuening on this topic? I know Xuening has done many work, different kinds of work, and this is one of the things he's done that we usually don't hear about. So, and it's nice that he offered this one. Yeah, but it's good that he actually show other simulations he's done. So that's relevant. Okay, so Xuening, thank you very much, and sorry for the delay, and thank you for testing with us about connection. Thank you.
No problem. Okay. Thank you very much. Hope I can visit you at some later time. Yeah.
Thank you.
Bye.
Okay. Bye.
So how many people in the room?
About 10, I guess.
Yeah, I think next time we probably should arrange the time with the
From 12:10 or something.
well, yeah, or we should do the booking a little better because it's a little bit embarrassing when we need to wait for so long. If we can actually try to see which day is better. So Thursday is Friday better for the booking?
Yeah, I think Friday is better.
Yeah, Thursday the ISM got stuck at
So in a sense, we nag.
Okay, so Koichi,
So yes, we might hold the same on Friday.
but is that
Yeah,
better? Is a Friday better in terms of room?
Yes, yes, that's right.
Better for room? Well, okay, so okay.
Could room 1203 be better than this in terms of availability?
Yes, there is no regular booking on Fridays at this time.
Yeah, but I was thinking all style, presential seminars. The room on 14th floor is better for a hybrid way.
Well, yeah, looks like Friday seems to be better for booking. No, literally the top one is in terms of booking before 12. Yeah. Phoenix 2.6, Phoenix 2.6.
You still recording?
Oh my God. How do we? It's gonna be recording in progress. How do I do that? Cocomelon. There's a Cocomelon.